Hey everybody, this is Miss List and I'm here with 3.10 from AP Chemistry, and this is a section that's on solubility. So solubility describes the extent to which something will dissolve in a solvent to form a solution. There's kind of three words we use to describe whether or not something can dissolve and the extent to which it dissolves. So if it can dissolve, it's described as soluble or highly soluble. If very little dissolves, it would be described as slightly or sparingly soluble. And if none of it can dissolve at all, it would be considered insoluble. Water is typically our solvent for most solutions in chemistry because it is extremely polar, and its polarity allows water to break apart ionic compounds very easily. So in this diagram, we see that the water molecules are surrounding the ions, but they're doing so in a very specific manner, and this is called an ion-dipole interaction. So the ion would be the sodium or the chlorine, the one with the charge, and then water is the dipole. In these pictures, for example, on the right with sodium, you can see that the negative part of water, the oxygen side, a negative pole, is pointing towards the sodium because we always want to make it so that a positive and a negative are being attracted to each other. So oxygen, being the negative side of water's dipole, is going to be pointed towards sodium. And then the opposite happens on the left with chlorine. With chlorine, we have the positive end of water pointing towards chlorine, again, making sure that we have that positive and negative attraction. Water can also dissolve non-ionic substances as well. And this is what happens in, for example, sugar. When something is covalently bonded, but it dissolves in water, one big difference is the molecule stays together. So here is a whole sugar molecule, and here is a whole nother sugar molecule. It's still interacting with the water, forming dipole-dipole interaction or hydrogen bonding interactions. But the key here is that we don't see any of the parts of the sugar particle breaking apart. And that's different than ionic compounds. When we have ionic compounds, like we saw a second ago with NaCl, it's going to break apart into individual pieces, sodium and chlorine. That does not happen when we have covalent bonded molecules. They still dissolve in water, again, because of water's high polarity and that interaction between dipoles. But we don't see them break into individual pieces like we do sodium chlorine. It stays together as one big part. So there are three steps that have to occur for a solution to form. And whether or not something dissolves depends on the energy of all of these steps combined. And we call them steps, but in actuality, they are all happening at the same time. But this is an easier way to describe how they are going to interact with each other. So the first step shown in the diagram is that the solvent particles have to space out from each other, and that requires energy. The second is that the solute particles need to come apart. And then the third step, they will all mix together to form our solution. And the difference is that energy is released when that happens. So we have the first two steps, energy required to separate the particles. Anytime you're making particles spread out, that's going to require energy. And then when they're coming back together, that is going to release energy. Now, how much energy is needed depends on what is the solvent, what is the solute, and their IMFs. The stronger the IMFs that are involved, the more energy will be needed to separate. So how we tell if the reaction or if the solution will actually form depends. You can think of it, if the solvent particles are more attracted to each other than they are to the solute, then they are not going to form a solution, because then all the solvent particles will just stay together and all the solute particles stay together. So if they're more attracted, if solute is more attracted to the own solute, then no solution will form. If the solvent is more attracted to other solvent particles, again, no solution will form. But if the attraction is strong enough between the solvent and solute particles, that's when we start to see these solutions form. And again, it's a series of steps. We have to look at the energy required to separate and when they come together to form the solution. Because sometimes when we form solutions, the solution gets warm. And so that means that the energy released is more than the energy that was required to separate them. However, sometimes we form solutions and it gets cold. So if that happens, then the energy released is smaller than the energy that was required. And so it's this kind of song and dance between energy, how much energy is required to separate them, are they attracted to each other, to determine whether something actually forms a solution. We'll talk more about energy in a later unit, but it is brought up here when we talk about solutions and IMFs. So I thought it was a good point to address it a little bit. Some other vocab words that we see when it comes to solutions is sometimes we call things that mix well together. We use that term we call miscible. I had a student a long time ago that used to say mixable, and that, if that helps you remember, great. And so that means that the solution will fully mix in one another. And these are typically terms that we would use for a solution that's made of two liquids. We would say they're miscible or immiscible. When we were talking earlier about soluble versus unsoluble, usually that would be a solid solute and a liquid solvent. So that's when we use the different terms, is depending upon what is our solute. So if it's a solid solute, we would use soluble or insoluble. If it's a liquid situation, we use the term miscible or immiscible. So miscible means they do dissolve in one another, like alcohol and water. And immiscible means oil and water. They will not dissolve in each other and they separate. So here we have a couple example problems that we're going to look at together that kind of decide or look at this solubility. So we have a chart here, and it says complete the table below about the general solubility of different compounds in water or hexane. So typically, water works best as a solvent when we have an ion dipole interaction. So that's going to be our ion dipole. And our hydrogen bonding and our dipole-dipole. Water does not work great with London dispersion forces because this is the only thing that nonpolar solvents experience. The rest of these are polar, and then we have an ion dipole interaction, which we talked about earlier with the salt. So I would choose yes in solubility for anything that experiences dipole-dipole or hydrogen bonding, because those are polar. Usually when they have similar IMFs, they're going to be soluble in each other. And then ion dipole is a special situation because of the ion's interaction with water. For hexane is C6H14, and the electronegativity difference between carbon and hydrogen is very small. It's around 0.4. And so we consider that to be nonpolar. And so if I have something London dispersion, that will also be nonpolar. Usually if it's two nonpolar substances, they'll dissolve in each other. So I guess it does say yes or no. So I would say yes for if they're both nonpolar or they're both polar. And I'd also say yes for water with ionic substances. Usually if they have opposite polarities, they are not going to dissolve in each other. So water being polar and something with London dispersion forces would be nonpolar. That's not going to work. And then similarly, when I have hexane, trying to go with polar things. All right, in the second question, it says, shown below are the structures of glucose and cyclohexane, and they want us to identify all the molecular forces in each compound. So for hexane, over here on the right, it's only carbon and hydrogen, so the only IMF that it can experience is London dispersion. When we have glucose, we can have London dispersion, we can have dipole-dipole interaction, and we need to check to see if we have some hydrogen bonding opportunities, and we do. We've got a hydrogen connected directly to an O in several locations with this OH group. And so any of the OH groups could participate in hydrogen bonding. And so this can definitely be listed as hydrogen bonding as well. So H bond. And this one's LDF only. One of the molecules is soluble in water and one is not. Which of the two would be soluble in water? Explain. So obviously the one that has similar polarities to water is going to be the one that is more soluble in water. So I would say glucose is soluble in water because both glucose and water experience similar IMFs. Typically, when we do explanations like this, we should talk about both compounds. That's a pro tip. And so I do need to say LDF, or sorry, let's erase that. I should make a comment here that cyclohexane is nonpolar and would only dissolve in something that also was nonpolar. All right, my friends, that is it for this section. Thanks for listening, and I'll see you next time.